Welcome to Lecture 12. In this lecture, we're going to apply the concept of flux to a variable electric field. Then we're going to use this idea and fully develop Gauss's law.
Let's do an example now of electric flux when we have a variable electric field. And for this example, let's consider something we know quite well, which is about a positive point charge. We know the electric field around a positive point charge is going to be variable. And we know that's the case because our expression for electric field around a positive point charge is E equals kq over r squared. That gives us the magnitude, and the direction is outward. R stands for the distance away from the charge, so r is a variable. And if r is variable, then E is variable. So here's our example. The positive point charge, E is a variable. We'd like to calculate the electric flux, so let's write down our equation for electric flux. Electric flux has a symbol of phi with a subscript of E. When we have uniform electric fields, we just do E dot A, but if we have a variable field, we have to do the integral of E dot dA, which means we find the flux through every little bit and add up all those bits. So when we have our symbol A or dA, that refers to the area of a Gaussian surface. So let's deal with that part next. If we have a point charge, those are assumed to have spherical symmetry. So our Gaussian surface is going to be a sphere. For our next step, let's draw the Gaussian surface. So that's going to be a sphere that's concentric with our point charge, and our sphere has a radius of r. So we're going to try and find the electric flux through that surface. When you're doing these problems, you should always draw your Gaussian surface. Always a good idea to label them too, just to make sure we're clear about what it is we're doing. Okay, now we'd like to calculate our electric flux, so let's write down our expression for electric flux again. Electric flux is equal to the integral of E dot dA. Let's see what we have to put in for each of these things. Well, let's think about the scalar product part first, because the scalar part is really important. We have E dot dA. So we know that E dot dA is going to have a magnitude of the magnitude of E times the magnitude of dA times the cosine of the angle between those two vectors. Since we're talking about the vectors, we've got to identify the direction of the vectors. So the direction of our electric field, we've already established that we know that that's radially outwards. That one's okay, we've talked about that already. What about dA? Well, dA is a small part of our Gaussian surface. So it's the area of a small part of the Gaussian surface. I'm going to go ahead and draw a little bit of our surface dA. So the entire purple line is the whole surface. My little blue box I just drew was a little bit of the surface. The magnitude of that area is dA, and the direction is straight out. It is a vector. Okay, so what you might notice here is that the electric field and the area are parallel. The direction of the area vector is straight out from the surface. We defined that already. So we'll write outward there too. So our two vectors are parallel. It means that the angle between those two vectors is 0 degrees. So our conclusion here is that these two guys, E and dA, are parallel. And this is why we chose our Gaussian surface to be a sphere. When you pick your surfaces to match the symmetry of your charge, then you'll always end up having your vectors either parallel or perpendicular, and the cosine part of your scalar product becomes easy to deal with. So that's why you're always shooting for that symmetry, is it because it makes the integral and the scalar product easier to evaluate. So cosine of 0 is just 1. We're left with the integral of the magnitude of E times the magnitude of dA. Okay, hopefully you followed that along pretty well so far. So let's start to deal with this part. Our electric field vector, or our electric field vector magnitude E, is constant if we're a constant distance from the surface. So everywhere on this purple surface, it all has the same value of the radius r because it's a sphere. So everywhere on this purple surface, E is constant. That means in my integral, I can take E outside. So we take it outside because E is constant with distance from the surface, or distance from the charge. No, actually, I think I'm just going to rephrase that. Constant on that surface. Because the Gaussian surface has a constant radius r. Yeah, that's a better way to say it. Okay, so the integral of dA is just A. What does A stand for? A stands for the area of the Gaussian surface. Okay, the area of the Gaussian surface is the area of a sphere. And the area of a sphere is 4 pi r squared. Okay, looks like we're almost ready to write down our result. This slide is after getting full, so we'll just move on to the next one. So let's keep going with our result. We said that the flux was equal to E times 4 pi r squared. Now, what do we know about E? Well, the magnitude of electric field is K times Q over r squared. Let's fill in that result. And let's remember K, Coulomb's constant, is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. That's a constant that we know the value for. So our electric field is K, that's 1 over 4 pi epsilon naught, times Q over r squared. And then we're multiplying that by 4 pi r squared. Let's see what cancels. So the 4's cancel, the pi's cancel, r squared cancels, and we're left with Q over epsilon naught. So the net electric flux is Q over epsilon naught. So this is the net electric flux through a surface, a spherical surface around point charge Q. And I suppose it's through a spherical surface of radius r centered around point charge Q. Spherical surface around point charge Q. Now this is a pretty interesting result. This tells us that our net electric flux phi, it depends on our point charge Q, and it depends on the permittivity of free space. I think that's actually pretty interesting. Let's ask a few questions about that result. Just before we get into our theoretical questions about that flux result we had, I'll post a homework question for you to do. This is a pretty straightforward plug and chug, so I'm not going to include it in the video, but I will post a solution if you want to check your answers. Okay, first question we'll ask, does the net electric flux through a Gaussian surface depend on the size of the Gaussian surface? So let's remember what net electric flux means. Electric flux is a quantity that's proportional to the number of lines cutting through a Gaussian surface. I'll just write GS for a Gaussian surface. So our electric flux tells us about the number of lines that go through that surface. So let's draw two Gaussian surfaces. So here's one Gaussian surface. I'll draw a sphere around my charge. I'll say it has radius R1. So the number of lines through surface R1 is 1, 2, 3, 4, 5, 6, 7, 8. So R1, 8 lines. What about if I draw a second Gaussian surface, but I'll draw it with a different radius. So I'll make a bigger sphere. This one has radius R2, and R2 is bigger than R1. How many lines cut through surface R2? 1, 2, 3, 4, 5, 6, 7, 8. Still 8 lines. Same number of lines, same flux. So the answer to our question would be no. The net electric flux through the Gaussian surface does not depend on the size of the Gaussian surface. Okay, next question. Does the net electric flux through a Gaussian surface depend on the shape of the Gaussian surface? That's a good question. Let's draw two Gaussian surfaces. My first one, I'm going to draw a sphere centered around the charge. It's got radius r, so this is my surface 1. How many lines cut through surface 1? Well, if we count them up, there are 8 lines. So surface 1, 8 lines. Now I'll draw surface 2. I'm going to make this one a cube. So in 3 dimensions, it's a cube. When I draw the side view, it's a box. So if I have a cube for a Gaussian surface, let's call that surface 2. Surface 2 also has 8 lines cutting through it. So our answer does the flux depend on the shape of the Gaussian surface? We see that regardless if we have a sphere or a cube or any other odd-shaped surface, we'll still get 8 lines cutting through the surface. So answer to that question is also no. Okay, one more question to go. Okay, last question. Does the net electric flux through a Gaussian surface depend on the location of the charge within the Gaussian surface? Okay, I'm going to do my two-surface approach. For my first surface, I'm going to have my charge, my Gaussian surface, as a sphere centered on the charge. So here's surface 1. It's not the best sphere I've ever drawn, but hopefully you kind of get the idea. So surface 1, we've got 8 lines cutting through that surface. Surface 2, I'll draw more of a sphere. I'll still draw a sphere as best I can, but my charge won't be at the center anymore. So now my charge is closer to one side of the sphere than the other. So here's surface 2. If we count the number of lines, we still have 8 lines, so we still have the same electric flux. So the answer to that question is no. Okay, but there is one important thing right here. Does it depend on the charge within the Gaussian surface? So that word within is important enough to get a highlight. So the net flux doesn't depend on the charge within. However, the next thing we're going to look at is, does it really have to be inside? So is the within part important? Okay, let's try and work on that question about the charge being within the Gaussian surface. And let's address that question by asking, well, what happens if the charge is outside the surface? So let's start by remembering our definition of total electric flux. It's a quantity proportional to the net number of electric field lines through a Gaussian surface. So if we take the number of lines that leave and subtract the number of lines coming in, we get the number of electric field lines through the surface, the net number through the surface, and that tells us about the electric flux. So let's apply it to our point charge. We know that electric field lines come off our point charge, radially symmetric in every direction. So I'm going to draw those electric field lines coming off everywhere. I won't write over my text very much. So this is what the electric field lines around our positive point charge will look like. Now we need a Gaussian surface. I'm going to pick some oddly shaped object, just kind of like a blob. Okay, and actually maybe I'll just trace that in a little bit darker so it's easier to see. So there's our Gaussian surface. Now, what can we see about the electric field lines? So let's deal with the electric field lines that pertain to the surface. So all of these that don't touch the surface, they can't make any flux through the surface. What about the ones that do touch the surface? Well, the line right here goes in, comes back out. That one doesn't contribute to the flux because we have one line in and one line out. Then we have a line in, which comes out. We have a line in, which comes out. We have a line in, which comes out, a line in that comes out, and a line in that comes out. Okay, so this is true for every electric field line from that point charge. Every single line that goes in also comes back out. Now, this makes sense as a result when we think about it. So we remember that electric field lines always start on a positive charge and they always stop on a negative charge. So for the Gaussian surface we drew, nothing starts or stops inside. So for any closed surface, if there is no charge inside, so that means if the charge inside equals 0, then that means that no lines start or stop inside. Another way to think about that is that every line that goes in also comes back out. That means that there are no net number of lines entering or leaving the surface, which means that our net electric flux is 0. So if the charge is outside the surface, then the net electric flux has to be 0 because any line that goes in also comes back out. Okay, let's do a big picture approach now and use that to finally develop Gauss's law. Let's ask what happens if we have many charges both inside and outside a Gaussian surface. So I'm going to start by drawing a Gaussian surface. I'm going to draw my Gaussian surface such that we have some charges inside the surface and some charges outside. So this green line is my Gaussian surface. Let's do a quick recap of some things we've said already. We've said if there's a charge outside, it doesn't contribute to the flux. If there's a charge inside, it does contribute to the flux, but it doesn't matter where it's located, how big the surface is, or what shape the surface is. So those are some things we've said so far. Let's apply some of those things. Okay, first of all, there's no flux due to the charges outside the surface. So we can cross those off. That's because any line, any electric field line that cuts through the surface, any line that goes in also comes back out. So that positive charge on the top would have a field line that went in and then went back out. It wouldn't have any contribution to the flux. So all these charges outside have no contribution to the flux. Okay, that part's dealt with. What about the charges inside? Well, let's think about them one at a time. So I'm going to call this top charge Q1. We know that this will have a contribution to the flux. And our general expression for that contribution would be the integral of E dot dA. And that's the electric field due to charge 1 dotted with the area. And the result we would get for that net flux would be charge 1 divided by epsilon naught. Okay, so that's the flux due to that charge. What if I picked a second charge? I'll call this guy Q2. Well, my net electric flux due to that charge would be the integral of the electric field due to that charge over the area of the Gaussian surface, and what I would get for my answer would be Q2 over epsilon naught. And remember, it doesn't matter where the charge is, it doesn't matter how big the surface is, or the shape of the surface is. The only thing that matters is that the charge is inside. That flux depends on the charge inside. Now, if I do this for every single charge, I would get a flux for each charge. So I would get flux for charge 3, I would get a flux for charge 4, I would get a flux for charge 5, and I would get a flux for charge 6. Then to get the net electric flux, I would add them all up. I would just do the sum of all those and I would get my total flux. So the total flux due to every charge inside the surface is my flux of 1 plus my flux of 2 plus my flux of 3 and so on. I'm a little bored with writing that, so I'll stop. So that would be Q1 over epsilon naught plus Q2 over epsilon naught plus Q3 over epsilon naught plus dot dot dot. And that would give me the net charge enclosed by my Gaussian surface, ENC stands for enclosed, divided by epsilon naught. So this is really important. This Q enclosed equals net charge inside the Gaussian surface. The word inside is really important, so I'll write it a little bit bigger and I'll underline it. Inside the closed Gaussian surface, because our charges outside don't count. All right, this, as we sum it up, brings us to Gauss's law. The net electric flux, through any closed surface is the integral of E dot dA, and that's equal to the net charge enclosed by that Gaussian surface divided by epsilon naught. This gives us a tool to find the electric field when we know something about the charge inside. So this is Gauss's law. Some things to comment on here. This is one of Maxwell's equations, so it's kind of neat that we're going to do a fair chunk of our course all based around one single equation. That's kind of neat, and we do that in physics all the time, like we do whole courses based on an equation. It's important to remember that flux can be positive or negative, but it's not a vector, it's still a scalar. Positive flux means more lines go out than come in. Negative flux means more lines come in than go out. So flux doesn't go in or out because it doesn't have a direction. That's what the positive and negative means. The last thing is that Gauss's law does give us a tool for finding electric fields using this integral form. However, it's really only useful when we have lots of symmetry, when we have integrals that are easy. It's true when our integrals are hard, they're just tough to solve. So we're going to do applications where the integrals are easy to solve.